Hello, everyone. We're just going to allow a couple more minutes for everybody to arrive. Just hold on for a moment and then Trevor will shortly give the introduction. So we will start in about 1 minute from now.
Okay.
Okay, thank you all for waiting. I think we will begin now. I'll hand over to Trevor for the welcome. Thank you.
Thanks very much, Rosie. Hello, good afternoon, everybody. I'm Trevor Hoy, Pro-Vice Chancellor of International and Sustainability. Nice to be able to attend this afternoon. You might be able to spot that I'm somewhat in the dark compared to the rest of you because I'm in China at the moment. And today I've been out with colleagues from Xinyan University looking at a place where 15 months ago, 30 people unfortunately lost their lives when a debris flow went through their village. And the local government have asked the obvious question, I suppose, how likely is this to happen again in future? What can we do to stop it happening? What are the policy implications of these sort of hazardous events, which I think leads very nicely into what this afternoon's session is about, which is the first in a series of sessions organised through Brunel Public Policy, which many of you will know, but many may not, is a unit that works across the university, directed by Professor Justin Fisher, that uses our research from across the university to help inform governments, government agencies, policymakers, legislators, regulators. And this series, Are Regulators Keeping Up with the Science, is exactly the sort of topic that we need to be thinking about, whether in terms of climate change, as my example from today is, or the other areas that are going to come up in the series. So what's happening in this series is that some of the most recent and ongoing and innovative research from Brunel that addresses areas that are of policy and regulatory relevance are going to be presented, and challenges and issues related to that will be discussed. Today is around net zero, our regulations and government investment keeping up with agreed timelines to meet net zero targets, which is a major challenge, and with a relatively new government and just finding their feet a little bit, perhaps now is a key time to be asking just those questions. The next two seminars, as you may have seen, one is around policy responses to rapidly evolving major health emergency on the 19th. Let's get this the right way around, on the 19th. And then the other one is regulation keeping up with developments and the changing use of online digital communications, which again is an extremely topical and fast moving area. So that's enough for me. I'm going to hand you over now to the chair for today's session, Dr. Alex Reep, who will introduce the speakers. Over to you, Alex.
Thanks, Trevor. And it's fantastic to be here and a pleasure to come and sort of chair this first session. How we're going to work it today is as Trevor mentioned, we have two fantastic speakers who I will introduce shortly. But at the end of the session, we will also be having a Q&A. And so at the top of your Teams page that you're watching this, there should be a Q&A section. And so if you've got any questions, feel free to put them there. And at the end of the session, we will put them to the speakers and try and see if we can get any answers. So first off, today, we have Professor Xinyan Wang, who's currently a research professor at the Centre for Advanced Powertrain and Fuels at Brunel University of London. He was awarded the prestigious UKRI Future Leader Fellowship back in 2020, and his research interests include advanced combustion concepts and novel engines with low carbon and zero carbon fuels. He's received over £4 million of research funding and has published over 60 papers in international journals and conferences. So, Xinyan, I will pass on to you for the first session.
Thank you, Alex. Okay, I'm going to share my screen. Can you see my screen now?
Yes, we can.
Okay, thank you. It's really pleased to be here to share our recent policy brief on hydrogen combustion engines. So first, a little bit background about the why we are looking at hydrogen combustion engines. Obviously, currently we are focusing on net zero targets, and I believe the net zero targets now drive the future development of all the sectors. So this graph shows the global temperature in, let's say, almost 200 years, and we can see the significant increase of the global temperature in in recent 30 years, as indicated by the red color. And now we believe there's a correlation between the global temperature as well and the carbon emissions. As you can see, in recent 70 years, we do see a significant increase of the CO2 emissions. And currently, for the Western countries, they almost most of them achieve the peak. And obviously, it's a matter of how to reduce the carbon emissions. But for the developing country like India and China, they still have a lot of CO2 emissions. And in the UK, the government has ambitious goal to achieve net zero by 2050. Obviously, there are some intermediate goal. For example, by 2030, they have to reduce the carbon emissions by 68%. But it's not easy. The main challenge is basically the CO2 emissions have been released by transport for a significant amount. For example, this graph showed the transport sector currently in the UK accounts for 26% of the UK CO2 emissions. People may argue, let's go for, let's say, electric. Here, this slide shows some data around the new car sales in the UK. You can see in 2022, there are a lot of data in this graph, but we may need only to focus on the number I've highlighted. Let's change to the latest point. For this one, it's a pure electric vehicle, which means it doesn't have a combustion engine. In 2022, it's around 16.6%. And in 2023, it is 15.4%. And in 2024, it reduces to 14.7%, which means actually currently there are over 80% of the new vehicles, they still have combustion engines and they still burn fossil fuels. Obviously, the limiting factors for EV is the cost and also the limited charging facilities. And what about these heavy-duty applications like aviation, agriculture, machinery, and also the marine vessels, as well as the gensets? They're still burning fossil fuels using conventional combustion engines. I will give you an example that for these heavy-duty applications, they are difficult to be used with the electric system. This figure showed the big vessel. You can see the dead weight and the cruising distance. If they use diesel as a fuel, it only accounts for 2.2% of total capacity. But if they move to battery electric method, obviously over 100% of the total capacity will be used to store battery, which means there's no room for any goods, which is impossible for applications. So if I summarize these findings, we can see for light-duty vehicles like passenger vehicles we drive every day, they may go for hydrogen fuel cell or battery electric vehicles. You will see the market will gradually increase. But for heavy-duty vehicles, they will be very difficult to use these electric system because they are relying on very higher energy density propulsion systems, and also they are very sensitive to the cost. So what do we need to do for the areas in order to meet net zero goal? So maybe we can draw some conclusions from existing alternative zero carbon propulsion system. For example, for hydrogen fuel cell, obviously they use hydrogen as a fuel, and for battery electric system, they use electric systems. And obviously we can make a combination of these technologies coupled with engine technologies. You'll be able to find we can actually burn hydrogen in engines, and also we can make use of the electric system to make it a hybrid or range extender. Then we can get the sweet spot to address these challenges for meeting net zero by 2050. And that's the area we're working on. But people may argue why we use hydrogen. If we have renewable energy, why we go for hydrogen? So this graph showed the renewable energy production at on different days. You can see they change a lot day by day because they are intermittent energy, and also they are highly relying on the weather. And the right graph shows the production of renewable in one day. You will be able to see on the daytime, the production of the renewable energy exceeds the demand, which means we have to store this energy. Then this leads to the next question: what would be the best energy storage approach? And from this graph, we can see actually the chemicals are excellent to store energy for long time, from days to weeks, and for large amount of energy. So that's the reason we look at hydrogen as an energy storage as well as a fuel for combustion engines. Because of this, there are a lot of developments across the world. Different countries have developed a different hydrogen strategy. For example, in the UK, we have a lot of policies and strategies. For example, the 10-point plan, the UK hydrogen strategy published in 2021, and the Energy Act, which has been put in place last year, and also the UK Transport Vision 2050. This is a relatively new policy developed by UKRI. I think they just released a couple of months ago. Then we need to understand why we put hydrogen in combustion engines. People always say, okay, combustion engines produce CO2, but actually it's not right, because engine itself doesn't produce CO2. It is a fuel. If we put fossil fuel into the engine after the combustion, we will have CO2 emissions. But if we put hydrogen or other chemicals like ammonia, and there are no any carbon elements in this fuel, then you wouldn't have any carbon emission. And another important factor is e-fuel. They produce from they capture the CO2 by using renewable energy. Then you will have CO2 emissions, but they will come back to the fuel, so it is net zero. And if we want to assess the environmental impact, we have to introduce the concept of life cycle analysis. So it not only consider the usage of the vehicle or the fuel, they also consider the production to the vehicle recycling. So the right figure show the result of some LCA analysis of different propulsion technology. For example, we can see the hydrogen fuel cell shows the lowest environmental impact in terms of CO2 emissions. And also we find that if we use hydrogen in combustion engines or low carbon fuel in engines, actually it produce very similar LCA CO2 emissions, which means if we use these low carbon or zero carbon fuels in combustion engine, it does reduce the CO2 emissions. And another advantage of a hydrogen combustion engine is the low cost. So the right figure shows a comparison of different propulsion technologies. The middle bar, green bar, shows a hydrogen combustion engine. Then the right blue bar shows a hydrogen fuel cell. You can see the total cost of ownership across 5 years. The hydrogen engine is much cheaper, almost half of the fuel cell technology. Here, the definition of total cost of ownership is addition of purchase cost plus the usage cost. For example, if we want to use hydrogen, the cost of hydrogen will be considered. The reason is for hydrogen combustion engine, it can use low purity hydrogen in combustion engine, which means we can drop the price for hydrogen. And also we can make use of existing supply chain for combustion engines so that we can overall reduce the production cost for engines. Actually, hydrogen combustion engine is not new. Actually, it has been used in very first combustion engines almost 150 years ago, but obviously it's only a part of the chemicals. In the last 150 years, actually, there are a lot of development, and in particular in 2000, different automotive companies like BMW, Ford, and the GM, and actually they started to look at the hydrogen combustion engines, but they didn't put it into production because of the limitation of the hydrogen storage and also the production infrastructure. But in recent 4 or 5 years, we can see significant increase in the interest from automotive companies, as shown at the right-hand side. And this slide summarizes all the recent R&D work by different heavy-duty vehicles. You can identify different brands like Cummins, and in the UK we have JCB. They all put a lot of efforts in developing hydrogen combustion engines. And at Brunel, we have started quite a few projects on hydrogen combustion engines. For example, the first one is a smart ground project in collaboration with a few leading companies. And we have set up our very first hydrogen engine test cell at Brunel. And the second project we are working on is supported by the Innova UK. They call it the CMDC, Clean Maritime Competition. And it was a diesel engine, then we converted to hydrogen operation. And also recently we started a new project on dual fuel. Basically, it was a diesel engine, but we keep on using diesel part, but adding a second hydrogen injector in the intake pod so that we can achieve so-called dual fuel combustion. For all the test cells, we have to upgrade our facilities to make sure the engine testing can be safe. So we upgraded our ventilation, we add hydrogen detection sensors, and they are all connected to an automated shutdown system. So when the hydrogen concentration in the test cell exceeds a certain limit, all the system will be shut down to make sure we operate the engine safely. Here are some key results. For example, this is a comparison of a hydrogen engine with a gasoline engine. Basically, we use the same engine but with different fuels. We can see on the left-hand side, the hydrogen engine can run very stably. Basically, the value for the upper part of the graph is smaller, means it will be more stable. And the blue curve shows the results from gasoline. Obviously, it can't run at very lean condition. I will mention lean condition at a later stage when we talk about emissions. And on the right-hand side, we can see the efficiency in general across all the engine load conditions. The hydrogen operation shows much higher efficiency than the conventional gasoline operation. And here we come to the emission part, because when we talk about hydrogen, people may argue it produces a lot of NOx emission, though it doesn't produce any CO2 emission. So in this graph, we can see when we move to the right-hand side, basically it's a lean condition, basically where we use additional air to dilute the combustion, drop the temperature of combustion, then reduce NOx emission. We can see hydrogen can operate at a very lean condition. If it is 3, which means the required fresh air is 3 times of the required air for complete combustion. So we can see when it is over 2.5, actually the NOx emission can be very low. But for the gasoline condition operation, it can't extend to very lean condition. And normally, actually, we run our gasoline at lambda 1. Obviously, it is the NOx emission is much higher. So we have demonstrated when we introduce lean burn technology for hydrogen operation, we can reduce NOx emission to near zero level. And also, we haven't used any after-treatment system for hydrogen operation. Here, on the right-hand side, we also show some other emissions, like CO2 emission. We can't see any CO2 emissions, and no CO emission, and no unburned hydrocarbon emissions. So in summary, hydrogen combustion engines produce zero carbon and ultra-low NOx emissions with superior engine thermal efficiency compared to the fossil fuel engines. And the combustion engines can be adapted to burn hydrogen and other hydrogen-derived fuels. And the existing supply chain of fossil fuel engine parts can be reused or repurposed, enabling a circular economy. And further R&D for advanced engine design and control strategies will be needed to improve transient engine operation, enhance durability, and increase efficiency to make hydrogen combustion engines an environmentally and financially competitive zero-carbon solution for transport application. And this R&D would be better targeted within a clearer regulatory framework. So with the support of the government, for example, by developing dedicated hydrogen engine program, and with a clearly defined regulatory framework, we'll be able to enhance the wider usage of hydrogen engines for net zero target, and also will be able to strengthen the UK hydrogen economy and in the same time create more jobs. So our recommendation would be, first, the UK government should recognize the important role that hydrogen combustion engines could have in replacing fossil fuel engines in order to meet net zero target. And secondly, for hydrogen combustion engines to meet their potential to strongly support the transition to net zero, the UK government should invest and support industry and research organizations in developing dedicated hydrogen combustion engine R&D programs. And lastly, establish regulations on hydrogen engine vehicles, and a clearer regulatory framework would encourage the private sector to invest further. And if you are interested with the policy brief, you can scan the QR code, then you can read the full policy brief. I think that's all from my side. Thank you very much. I look forward to your questions.
Thanks, Xinyan. That's fantastic. And so for all of you watching, again, if you have any questions about the presentation, please feel free to go and put them into the Q&A tab up the top, and we can answer and have a discussion at the end of the session. Next up, we have Dr. Ioana Pisica, who is a reader in energy and power engineering, specializing in smart grid technologies, renewable energy integration, and the digitization of power systems. Her research focused on enhancing the efficiency and resilience of modern power networks with innovative grid solutions. Dr. Pisica is actively engaged in both academic and industry collaborations, aiming to bridge the gap between cutting-edge technology and practical implementation in the energy sector. So, Ioana, it's over to you.
Thank you very much. As the introduction from Alex said, this presentation will be from the perspective of energy and power grids. And our goal for net zero transition implies a sweeping change across the entire energy sector. And I will briefly go through what new technologies can offer, the major hurdles in grid modernization, the evolving infrastructure requirements for this transition to happen, but from the policy and research points of view. And each of these areas are fundamental for the smooth and effective transition to net zero. To start with the challenges, of course, grid modernization is not without its challenges. First of all, reduced inertia, costlier voltage management, thermal constraint management issues are just a few of the key issues and the key obstacles in transitioning to net zero. And as we incorporate more renewable generators, which are mostly asynchronous, these challenges become more and more complex and more demanding, and they require more innovative solutions. So this is where the research comes in, but they also require regulation and policy making in order to be implemented effectively in the real world. We also have another issue, the fact that generation is mostly located at network extremities. So we have the offshore wind from Scotland, and our centers of demand are in the south. So that creates bottlenecks in the transmission of this renewable energy, clean energy to areas of consumption. And this hinders the transition to net zero and creates technical difficulties in terms of thermal constraints for our assets, so power lines and transformers. But also there is another key area in which we have challenges, which is the fact that when we have a reliance on renewable energy, mostly solar and wind, if we have long periods when the wind doesn't blow or the sun doesn't shine, then we have to deal with these periods where we don't have output from the generators. And while these long periods of non-generation can be managed or mitigated through long-term storage solutions, flexibility schemes, digitalization, the thermal constraint management has to be achieved with low carbon technologies. Otherwise, we cannot achieve net zero. So we have to make sure that we are adapting our thermal constraint management to encourage the use of low carbon technologies. And one of the difficulties is the fact that combined cycle gas turbines are used for thermal constraint management via the balancing mechanisms. And we must support the transition to hydrogen to power or power carbon capture and storage for unabated gas generators in order to be able to have ancillary services that are decarbonized. And of course, for this, we need the infrastructure across the hydrogen value chain that has to be accelerated. And of course, we have to also make some allowances and some modifications to the capacity market in order to allow already enrolled gas turbines that are unabated to switch to hydrogen to power, for example. Another issue is the fact that we have high balancing services use of system costs. And one area that has been looked into for a while now, but has not been implemented yet, is the locational marginal pricing in order to reduce this cost. And another issue is the fact that the capacity market is focused on winter evening peaks, so looking at the demand during the highest points in the year when we are experiencing a lot of demand. But that becomes now irrelevant because now we have to look at the weather conditions and to see what output we would have from our renewable generation. Further, the constraint management is done through curtailment of generation. So that means that if the wind is blowing, but we don't have anywhere to evacuate that power in our network, we simply stop the generation, which is, of course, a waste of resources. So the policy has to support the opportunities for storage rather than curtailment, and hydrogen is a good example for storage. There are round-trip efficiencies quoted that are considered to be low still, of 18 to 35%. But if we take into account the fact that this energy would be lost anyway because of the curtailment, then hydrogen becomes a good proposition. And new metrics should be used. So I'm proposing the levelized cost of energy or any kind of metric that takes into account the life cycle emissions of technology. Another challenge comes from lack of public acceptance and understanding of new requirements of low carbon energy systems, because we are used as consumers to have this commodity. And we see here on this slide two different facets of the community engagement. So the one on the left-hand side is from a good practice guidance that was published by BASE before it changed the name. That was in 2021. And on the right-hand side, we have the view of other communities where we see here that the views are not very favorable and people are usually reluctant in accepting changes in their backyard, so to speak, for energy infrastructure. However, energy infrastructure is required in order to keep on providing energy to the consumers. So the public engagement and the acceptance has to increase drastically. Moving now to what emerging technologies can offer. First of all, digital infrastructure is the backbone of energy systems in a net zero operability. And we have asset monitoring, real-time control. We have algorithms that rely on sensors and data and complicated algorithms to give us the most efficient use of resources, which can bring benefits like self-healing networks and real-time situational awareness. We can include heat pumps to decarbonize heating. We have vehicle-to-grid optimization, and this brings with it cybersecurity issues. So this has been recently taken into account, and there are now studies being done in academia about cybersecurity for power grids. But when it comes to the policy is a bit behind on that, and we don't have real-life implementations that look into details in these aspects. What is important to mention here is the fact that local flexibility can unlock below £1 billion per year by 2050. But if we have a portfolio of flexibility services enabled by the sensors, data, algorithms, and digitalization in general, then we can enable around 16 billions per year of benefits, which is an important part. I mentioned electric vehicles and vehicle-to-grid. There are efforts to note in terms of transport decarbonization. So we see here three of them. We have the transport decarbonization plan, the future of freight plan, we have the electric vehicle infrastructure strategy. So we see that there are policy and regulatory efforts that are being made towards decarbonizing transport. Further, making the case of what the new technologies can offer, data-driven models can help us in forecasting demand and to design those flexible network solutions that can bring the benefits that I mentioned earlier, estimated in some studies to £16 billion per year. Also, asset investment can be reduced by optimizing the way we are managing our network. And another a tool that we can use is dynamic line rating, which can help with the congestion management that I mentioned earlier, and also to reduce network reinforcement costs. So we have mechanisms through these new technologies that are helping us to decarbonize the network and to maintain security of supply. However, research is again ahead of policy in this area with few implementations in real networks. Of course, our network and our infrastructure requirements are evolving. And please bear with me with this analogy. So if we have this much, the existing installed capacity, which is around 112 gigawatts, and we add on top of that the theoretical additional capacity needed in order to achieve net zero by 2050 of 275 gigawatts. This is from the future energy scenarios leading the way. The values are taken from there. If we look at the queue of network connections, then we actually see that we have more than double of projects waiting to be connected to the network compared to the requirements for our networks. So in fact, we have dropouts from that queue of 60 to 70% due to different factors, but still the amount of connections required is very, very high. And in order to make sure that we allow the connections for projects that are most viable, there are efforts made in the policy pathways by the government and by Ofgem in order to try to reduce the queue and also reduce the time that it takes for a connection to actually be implemented. And we have some strategic spatial energy plan. We have the Clean Power 2030. We have the Energy Networks Association Strategic Connections Group that are working to achieve this. But from the research part, we identified that people, physical devices, and digitalization are cornerstones in being able to implement this policy. And we have a new way of managing connection requests. I will not go into detail. You have details here on how to access the document. It was published this month, so it's fresh off the press. And what we have to do further is to make sure that we adapt the markets as well in order to incorporate all the technologies that are needed to decarbonize the energy system. And with that, we can turn around these contradicting arrows, and we can see what has to be done in order to decarbonize the energy system. I will not go through this now, but I want to let you go with one point, which is the fact that energy is a societal benefit and requires educating the general population. So we need all of us to do our part in order to help with the decarbonization of our energy system. And with that, I would like to thank you for your attention, and I welcome questions.
Brilliant. Thank you, Ivana, for that. So again, any questions from that, please put them into the tab. We've had a few come in already, so I think we'll have a good start. So I think the first one, Xinyan, really goes to you. It's from Ahmed Zuba. The Clean Power 2030 Advice on Achieving Clean Power for Great Britain by 2030 report identifies hydrogen combustion engines as a potential zero carbon solution for larger vehicles and machinery. However, scaling this technology would require complex supply chain adjustments and substantial infrastructure investment for hydrogen production and distribution. How do you propose these challenges might realistically be addressed to meet the 2030 target?
Yeah, thank you for the question and also the comments on the report. Actually, I think a few UK policies have included the hydrogen combustion engine as a potential solution to decarbonize transport, in particular for the heavy transport. And in terms of your question, I think it's very it's very difficult question, and also I think it would be very difficult if government doesn't provide enough support for the setup of infrastructure, no matter it's hydrogen combustion engines or hydrogen fuel cell or battery electric vehicles. So I think it's really important to understand that for hydrogen combustion engines, as far as I know, and also from our research, it can be a very cost-effective way to reduce CO2 emissions. As demonstrated from our ongoing projects, we can run hydrogen combustion engines with low purity hydrogen, which means we can significantly reduce the cost of hydrogen production. And I know there's a lot of discussion on alternative solutions. And for example, hydrogen fuel cell, then we believe compared to fuel cell, the advantage of running hydrogen combustion engine is to make use of this existing infrastructure. So for any engine OEM, they doesn't really need to invest a lot of money and time and efforts, and also recruiting more engineers for developing new technologies and new infrastructure. They can business as usual, but obviously they have to invest some money or staffing to adjust their production line for the hydrogen engines. But I think, as mentioned at the right beginning, it's very challenging to meet 2030 goals. Yeah, considering time, it's already 2024. We are going for 2025.
Thank you. Yes, I think yeah, the 2030 deadline has been coming up and it's sort of been jumping out quite a lot now, considering where we are. So yeah, trying to hit these things at 2030 is going to be challenging without significant investment. So I think that's a very fair point. Considering the need for all of the supply chain adjustments and the amount of infrastructure that we need to put in for this, especially for if you're going to make it green hydrogen, the sheer amount of renewable generation you're going to need, which might be more than even Joanna on your presentation, you were sort of mentioning the need to get to 2050. How do you sort of feel that looking for this to be able to generate this kind of infrastructure quickly, if we were going to hit that, how would you sort of think that would be a good way of going? Where would you sort of say would be the best places to look for that?
Yes, so I will take this one, even though in the chat it says it's for Xinyan. First of all, we can do gas pipeline retrofitting, which is a faster solution to building a transmission system for hydrogen. But we need incentives for hydrogen production. So we need subsidies at the moment in order for the technology to become viable. We did it with renewable energy, so with wind turbines and PV panels. We did it with electric vehicles, and now we need it for hydrogen as well in order to move the technology along and to move the investment. But what is more important is to build up the markets. So to close the loop, it's not only producing it, but building the need of having this hydrogen. And we can use it for heating, we can use it for particular cases in transport, and of course for hydrogen to power where the combustion comes into place, and Xinyan can add things here.
Yeah, I think you mentioned a very important point. So once it's kind of a chicken and eggs. So if you have like a low cost technology which can make use of hydrogen, then all the hydrogen supply chain around the production side will play their role. Then you will have like a kind of a closed loop, as mentioned by Iona, so that you can really push the development of the hydrogen economy, then obviously gradually achieve net zero goal.
And I think, yes, that's to add, I think that's one of the nice things seeing in the Chancellor's budget the other week, seeing that the hydrogen allocation round one were actually still in the budget and still being funded. So actually seeing that there is more government, well, not more government support, but government support still in this area to try and help push this along, I think, yeah, as you say, is very important.
But if I may add something as well, the timeline is very short. We are almost in 2025 and we are talking about 2030. It's very little time. So one thing that has to happen very, very fast is, as I mentioned in my presentation, public acceptance. We need to understand that we cannot continue in the same way as until now, and we all need to change our perspective on the energy system.
I think, yeah, completely. It's been seen a lot recently with the developments going in for the very, very large scale solar farms all over the UK. Seeing how there has been some public acceptance, but as you say, a lot of public not wanting it in their backyards, which always causes issues. So I think, yes, it's very key to being able to actually hit this sort of challenge. Brilliant. Next question, again to you to start with, Xinyan. What kinds of regulation might be needed for hydrogen combustion and engines, and why?
Yeah, it's a good question. So first, obviously, for any engines vehicle, we have to look at the emission regulations. So we can see actually there's new regulations for vehicles, Euro 7, but there's no dedicated regulations for hydrogen vehicles that we have to respect for. And also in terms of hydrogen, because it's unique properties, right? So we have to consider the health and safety regulations. Actually, we have put in the response to a recent government consultation on non-road machinery, mobile machinery last year. So basically for this kind of consultation, the government needs to get the inputs from the public on potential regulations on around some applications. In this case, is a non-road mobile machinery. So we can see there's some policy gap, the regulation gap, because currently for any hydrogen vehicles, they couldn't be used on road. Then they would need to develop the regulation so that the industry can basically develop their technologies to meet these regulations. Then they can make sure their vehicles can be used on the road. So basically, that's what happening for the hydrogen combustion engine vehicles. There is no such defined regulatory framework that the companies need to respect, and when they develop the vehicles or technologies, they have to have these kind of reference regulations so that it makes sure they meet the regulations.
And how do you sort of see the UK regulations being? Do you see them being any different to what's being done in other countries, so the rest of the EU or the US or China and sort of other large companies that are looking to develop this?
I think the government now is at least is working on the narrowed mobile machinery, because I think there's some push from the industry, and but obviously I think we should also do for other hydrogen powered vehicles, for example, the passenger vehicles, the heavy duty vehicles, and I can see there's some work in other countries, and they are trying to develop the small scale demo. Then they can get the kind of evidence to develop the regulations. Obviously, I think we have to do here in the UK so that we can basically gradually develop these regulations.
Yeah, and I mean, yeah, so for the engine side of things is one thing, but looking into sort of the regulations for much larger scale gas turbines and sort of the regulations and things like that. I don't know, Ioana, from sort of the work that you're doing to bring you into this one, whether looking at larger scale regulations for gases for the likes of gas turbines would be any different to the kind of work that's looking to do already?
Well, yes, to an extent it would require some differences. But the idea is that this is a fine line, I think, and the large gas turbines are very important for the power system, because they give this inertia that I mentioned earlier, the rotating masses, and they help with the stability of the system. So it's not only a matter of cost, it's a matter of security of supply. So when regulators make plans, they should focus firstly on the security of supply and then on the other aspects, even if that means delaying the decarbonization of the system. But we have seen the geopolitical context, the recent one, that showed us that security of supply is very, very important.
No, that's great. And staying with you for the next question, we've got the Clean Power 2030 Advice on Achieving Clean Power for Great Britain by 2030 report highlights the urgent need for modernising the grid to accommodate renewables, balancing the demand of consumer flexibility, infrastructure investment, and energy security. Given the historically low level of consumer engagement in the demand-side flexibility, what practical measures would you suggest encouraging participation across various consumer groups? I'll start with that, and then I'll move on to the next part of the question afterwards.
Yeah, that's a big question, not only in length, but also in depth and what it entails. So we see that the consumer flexibility is lagging. And again, it comes from the lack of acceptance, but it comes also from the lack of push from the government to get consumers more involved in managing the power networks. So it has to be done at government level, and we have to push for this transition to happen.
I think, yeah, and I think a lot of the time as well, especially when you're talking about energy, a lot of especially the private investment that's going into it can be a little bit closed. And so I think there's a lot of the chance where consumers actually want to have companies be more open about everything going on with their system, whether if it's a local system, if they'll get access to it and then be able to shrink their own bills rather than just putting it to the grid. I think that's probably a lot there to do with it as well, to try and get more support from local communities that are having larger scale generation facilities put near them.
Yeah, it's showing them the benefits.
Yeah, definitely. And the second part of the question, considering the report's emphasis on a significant expansion in transmission infrastructure, how feasible is it to meet this requirement within the proposed timeframe, and what role might emerge technologies such as AI play in supporting these efforts?
Well, the delays of 6 years plus for connections waiting to happen are not very good news, and I don't think they will change overnight. The NISO efforts to clear the queue and to put at the top of the list the projects which are the most ready to be implemented is a good way to move forward. However, it opens up some questions about the criteria used in order to prioritize some of these projects. Now, NISO are talking about some technology buckets and putting priorities into those priority projects into those buckets and so on, but I don't think it's yet transparent enough. Of course, it hasn't been finalized yet. It's due to be finalized at the end of this year. So let's wait and see what they say. But at the moment, it doesn't look like it will be a very, very transparent process. So I think that we will slip with the timeframes, even with the NISO modifications to the connection management procedure. In terms of artificial intelligence, I don't see it playing a big role at the moment in the power networks, in the connection and in the transmission expansion. I mean,
what about in sort of the balancing of the system then, to be able to have AI working on turning on and off systems as they need? Do you see that as coming in later on?
I meet dispatchers from the control room, and I know that they are very reluctant to change anything in their systems. So I really don't see that happening. We are using a lot of AI theoretically to find out the optimal expansion plan for different systems. But I think that once again, the research is way ahead of the actual implementation.
That's fair enough. And I think we've got one more question, which I think, looking at the time, so we can get through. You mentioned locational marginal pricing. What's the difference between the UK and other countries?
Right. So the UK doesn't yet have implemented the locational marginal pricing, but we are looking into the benefits of it. We have a national pricing at the moment, like Germany, for example. There are countries with zonal pricing like Denmark, Norway, Italy, Sweden, where they have a large share of renewables, so it works. And then we have nodal pricing, which is the most granular one in the United States, in some of the states, in Ontario, in Canada, and in New Zealand. So there are models to look at when we switch eventually in the UK.
Eventually. That's really good to know. Well, I think from the time we've got, I think I'll say thank you very much now to our two speakers, Professor Xinyan Wang and Dr. Ioana Pisica, and pass on now to Rosie to close the session, if you can.
Hi, and thank you all for coming. So, hi, I'm Rosie Smith. I'm the manager of the Brunel Public Policy Unit who organised this session. So, I'll firstly say thank you to our speakers, Xinyan Wang and Ioana Pisica, for thought-provoking talks that highlighted important areas where recent and ongoing science and technology advances could help the UK to reach net zero targets, whilst also highlighting the scale of the challenge for scientists, industry, government and the public with the deadline so soon. A big thank you also for our excellent chair, Alex Reep, who's the Royal Society Entrepreneur in Residence at Brunel. And for him and the audience for really helping us to explore the issues raised, especially the challenging timeline, which will need acceptance and engagement from both policymakers and the public if we're going to have any chance of meeting them or getting close, I guess. So yeah, thank you all. And just before you all go, to highlight the context of this event today. So we in Brunel Public Policy decided to run an event series on Are Regulators Keeping Up with the Science? Because we think there's a lot of exciting and relevant research taking place in Brunel that could have a positive impact on policy making and regulatory processes. Our next events will explore policy and regulatory responses to major health crises through the lens of COVID-19, and how to keep up with development and changing ways that society engages with online digital communications, such as social media. Registration links with further details I'm going to drop into the Q&A right now. And finally, thank you all for joining us today. And yeah, that's all. Thank you all. Bye-bye.
Thank you. Bye.
Thank you.